is half-life. So the question becomes this: what is so big about this idea of half-life that it could radically change your views on whether or not we should use nuclear power? So guys, I suspect the answer is going to be no, but let me ask you a question. Do you remember when we first got introduced to the idea of half-life over the last couple days? Do you really remember? When was it, Caden? It was the Eyes of Nye video, and who was it that talked about it? Do you remember? Do you remember that guy that kept calling us a species? Do you remember that guy? Yeah, and I'm sure you don't remember this, but he was talking specifically about plutonium. Plutonium's the most dangerous thing we've ever created. It'll probably be our demise, and he went on and on. But guys, he talked about the half-life of plutonium. Do you happen to remember the number? Wow, good on you. Yeah, guys, it was actually 24,000 years. Not a number that you need to know. But guys, this is where the conversation began in the Eyes of Nye video, because this guy that kept calling us a species, talking about plutonium, pointed out that the half-life of plutonium is 24,000 years. And then they got into a conversation about what that means, and most of you just sat there and watched and nodded your head because you have no idea what half-life was all about. Well, guys, we're going to change that in just a minute. So here's what we're going to do. I'm going to define half-life for you. Then we're going to go back and watch that little snippet from the Bill Nye video. And guys, for some of you, this is going to radically change your opinions on nuclear power generation. Then once we've got all these ideas pulled together about what half-life means, we're then going to look at it graphically, then we're going to look at it logically, and then we're going to wrap up the day, and you should get your homework done today. So guys, in order to get started, here's where we're going to begin. You need a definition for half-life, and I would strongly encourage you to get this in your notes. So guys, it goes like this. What is half-life? Well, guys, half-life is a measure of radioactivity. By the way, guys, as you're writing this down, I forgot to mention to you the test that you have on Monday. Guys, please print the study guide and study for this test. If you come into this test cold, it's gonna bite you. There's a lot of material. It's all the way fission, fusion, history, alpha, beta, gamma decay, fission, fusion, half-life. Guys, this is a big unit. Make sure you go study. Okay, so half-life is a measure of radioactivity. And guys, remember when we say radioactivity, we mean decay. So reviewing for the test, what are the three types of radioactivity that you guys know? Alpha, gamma, and beta. Okay, alpha. So that's what we're talking about. So when we talk about half-life, we're talking about how fast does something go through alpha or beta or gamma decay. But guys, it's not quite that simple, and here's why. Guys, when a substance goes through alpha, beta, or gamma decay, it is completely spontaneous. The atoms in these materials just spontaneously break apart or decay. And guys, the tricky word in this is spontaneous. It means happen without warning. Just all of a sudden an atom goes, woohoo, and it decays. And that creates a problem. The problem is that we can never tell when an atom is going to decay as an individual. So we can't tell when an individual atom is going to decay. So how can we measure how fast something happens if we can't tell when any individual atom is going to do that thing? And guys, the answer is we deal with fractions. So while we can't tell when an individual atom can decay, we can tell when a fraction of those atoms are going to decay. And guys, if you're really paying attention, you want to take a guess as to what fraction we're going to talk about? Half. That's where the name comes from. So guys, this is where we're at. Half-life tells us it's a measure of radioactivity, alpha, beta, gamma. The problem is that this alpha, beta, and gamma happens spontaneously. Because it's spontaneous, we can't tell when an atom is going to do this. So instead of figuring out when individual atoms are going to do this, we figure out when fractions of them will do this, and our fraction is going to be a half. Guys, this then leads us to our definition of half-life. Half-life then is the amount of time that it takes for half the atoms in a radioactive sample to break apart. It's all about half. So guys, once you've got this down, we're going to talk about this in a visual way. I'll show you in a minute. And this will help you understand. Then guys, we're going to go back and look at this Bill video again and see if you understand it better. You will understand it better as a result. So once you're caught up with me to here, guys, just settle in and let's actually help you understand what we're talking about here. You guys all caught up? Not quite yet. Are you good? Hayden, you're good. Joe, you okay? Faster, Joe, faster. You're good. All right. You guys okay? So guys, let me help you understand this idea of half-life. And frankly, I was going to use uranium, but frankly, I'm running out of latex gloves, and I'm sort of sick of touching that. So guys, here's what we're going to do to help you understand the idea. This is just a rock that I stole out of the planting beds out in front of the school. But guys, we're going to pretend that this rock is a chunk of plutonium. So guys, watch closely, and I think this will really help you understand. So this is the idea. Guys, this rock, as it sits right here, represents plutonium pulled out of a nuclear reactor. So this is pure plutonium pulled out of a nuclear reactor. Hey, we're talking about nuclear power. Plutonium. And actually, this really is uranium. Yes, but frankly, we have so many of them, we're probably not even going to notice if you just stole one.
Yeah, but I can just transfer.
Let's do this. When we place an order for another, because you can see we buy them by the truckload. When we place another order, I'll let you know, and you can slip us money for a package of them. So.
I'm an honest man. I want Matt to know that.
I know. Matt is a witness.
I've got a lot of problems in my life. A lot of them.
Thievery is not one of them.
All right, thanks.
See you, buddy. All right. So, guys, plutonium pulled right out of the reactor. Okay, now this is how this is going to go. We're going to allow the floor to represent time. And then, guys, this wall over here by Matt, right here, this is 0 plutonium, completely safe. Everything's done. All the plutonium is gone. Now let's talk about half-life. What's the half-life of plutonium? 24,000 years. Now, guys, watch. So this is all plutonium pulled out of the reactor. And then we let it sit in a swimming pool. We let it sit for 24,000 years. That's one half-life. How much of this is still plutonium? Half. That's the idea. Half of it is still plutonium. But now, guys, watch. After another 24,000 years, does all the plutonium go away, and this is safe and this is done? That is not how half-life works. So, guys, how does half-life work? And here's the answer. 24,000 years, half of it is now plutonium. But guys, what's going to happen in the next 24,000 years? Half of that is going to go away. How much of this is now still plutonium? A fourth. And then 24,000 years later, an eighth. And then 24,000 years later, a 16th and a 32nd and a 64th and a 128th and a 256th and a 1024th. But guys, will we ever get to the wall? No. So mathematically, ready for this? Mathematically, what does that make the wall? An asymptote. We just did math right there, y'all. Guys, that makes the wall an asymptote. All an asymptote is a place that numbers never get. So guys, this is an asymptote, which means this never becomes this will always contain some plutonium. But guys, it gets worse than that. Check this out. Follow the laser. So this is plutonium. And guys, you should know the answer to this question. Follow the laser. So this is plutonium. But guys, plutonium is an alpha decayer. So this thing gives away alpha particles. So if this gives away alpha particles, does the atomic number go up by 1 or down by 2? Down by 2. And look at what it turns into. Uranium. So guys, this gets even scarier, because check it out. Pure plutonium. 24,000 years later, how much of this is still plutonium? Half. But what's this? Uranium, and that's deadly too. And 24,000 years later, now a fourth of it is still plutonium, and 3/4 of it is uranium. And it just keeps on going. Guys, you understand how this is a little more complicated than maybe you thought? So now, guys, let's make sure, just before we move forward, do you all then understand these ideas? Don't write them down. This is what you've got to understand. Where do the radioactive atoms go after they decay? And guys, the idea is this. After each half-life, 1/2 of the original sample remains. Does that make sense? But now we understand the scary other side of this, which is that the atoms that are decayed become other elements, and many times those other elements are also dangerous, like plutonium becoming uranium. So guys, anything there that you need to talk about? You guys good? All right. Now, let's watch this video again, guys, with new eyes. It's only 1.5 minutes long. But as Caden pointed out, this is the place where we first ran into the idea of half-life. So guys, we're going to play the video, but you are now going to understand this in a way that you didn't a couple days ago.
Plutonium is the most dangerous thing that human beings have ever made. Probably be our demise. A millionth of an ounce, the size of a speck of dust, inhaled will cause lung cancer.
Okay, let's start over. Here we go.
Plutonium is the most dangerous thing that human beings have ever made. Will probably be our demise. A millionth of an ounce, the size of a speck of dust, inhaled will cause lung cancer. A few pounds, the size of a grapefruit, you can hold in your hand, will bring down a city using a nuclear weapon. And it has a 24,000-year half-life.
There it is. 24,000-year half-life. This is where Bill then does his best, and a good job to explain it.
We measure radioactivity in what's called half-lives. You see, the atoms in radioactive material spontaneously just break apart or decay. And we can't tell when an individual atom will decay, but we can tell when a fraction of them will. So a half-life is the amount of time it takes for half the atoms in a piece of radioactive material to break apart. Now, plutonium has a half-life of 24,000 years. So let's say this...
Okay. So guys, given what you now understand about half-life, let's talk about this visual that Bill put together, just to make sure we understand. So guys, what does the red food coloring represent? Plutonium. The darker the red color, the more plutonium is in the sample. Now, what do these cinder blocks represent? Half-lives. So every one of those cinder blocks represents 24,000 years. Now, guys, this. How is this bottle on the right different from the bottle on the left? And the answer is it has been diluted by half. In the same way that our rock breaks down by a half, and then a half of a half, and then a half of a half, and so on. Guys, the water inside this bottle is being diluted by half. So this is half as red as this. This is half as red as this, or a fourth as red as that. This is half of this, or an eighth of the original sample. So it goes half, fourth, eighth, 16th, 32nd, just like the stuff on the floor. So let's let Bill take it from there.
Headwaters, the plutonium in a spent nuclear fuel rod fresh from the reactor. Well, after one half-life, 24,000 years, diluting this water by half, it looks like this. After two half-lives, 48,000 years, it would look like this. After 10 half-lives, 240,000 years, the water starts to look pretty clear. Now, plutonium is notorious. It's especially radioactive. It's 20 million times more radioactive than uranium dug from a mine. You see, we're not talking about potato salad left out in the sun. We're talking about plutonium. Now, the legal requirement for storing this material is only 10,000 years. That would be over here someplace. That's not even half of a half.
All right. So guys, let's go back and let's pick this apart. So I have some questions for you. So first of all, this. Given what you now understand about this thing that Bill put together, let me ask you a question. If the red food coloring was poisonous, would any of you be willing to drink the water in any of these bottles? No way. Guys, I can even see on a not very good video that there is still a tinge of red in this bottle. You can still see the plutonium. But guys, think about this in terms of time scale. Let's use easier numbers and say the half-life is 25,000 years. So guys, this would then be 25, 50, 75, 100, 125, 150, 175, 200. Guys, that's 225,000 years from now. And you've said that if the red stuff is dangerous, I don't want anything to do with it. Guys, we are talking about unimaginable amounts of time. But it gets even worse than that because we're not just afraid of the red stuff. Because the red stuff, plutonium, turns into uranium, and that's deadly too. And the uranium doesn't even have a color in this picture. But guys, this is where this gets a little frightening. And Michael, this is to your question earlier. Because the question is this. What does Bill's hand represent? Say it again. 10,000 years. What is 10,000 years? What is 10,000 years? That's how long we've got to be able to store nuclear waste. Now guys, do you remember from the video, where did that number 10,000 years come from? Did any of you remember? Guys, this is sobering. This is where 10,000 years came from. So you understand that we do now take the water, the rods out of the swimming pool, and we store them in those columns that are made of concrete and steel. So that right now is our long-term storage solution. But as they were building and testing these containers, they found that the containers would probably crumble in 11,000 years. So our government said, okay, if these things are going to crumble in 11,000 years, let's make the legal storage limit 10,000 years, and then our containers meet the limit and we can put stuff in them. You see the ridiculousness of that argument? And guys, if you look at the science, you understand that it's completely stupid. It has nothing to do with science. The half-life of uranium or plutonium is 24,000 years, and our government is saying we've got to be able to store it for 10,000 years, which isn't even a half of a half-life. It's not based on science. It's based on us fudging the numbers so that we can stick it in those containers. You guys see the problems with this? It's a mess. It's a mess. Now, guys, the question that you've got to figure out is it big enough of a mess for us to not want to continue to use nuclear or, in the case of Green River, build more nuclear power plants? So, guys, now that you have a better understanding of this, I suspect that for many of you, it's going to become a part of what you write about. Even if you're still pro-nuclear, you're going to have to address this in your antithesis because this is a problem. And you're going to have to figure out how to deal with it. So, guys, anything there? Any questions, things that you want to explore or talk about? You okay? You guys good? Okay. Okay, so guys, this then is how we're going to move forward. We now understand this conceptually. We now understand this in terms of our rock breaking down into halves of halves. But guys, what we need to do now is we need to understand this idea graphically. Don't put this in your notes, but guys, join me here for just a minute. You understand that one of the things we're going to be working on throughout the year is getting you better at reading graphs, because that's what the ACT in science is all about. So guys, when I pulled these notes together a couple years ago, I'm like, man, what a great opportunity to show my students graphical representations of half-life. And so I went out on the internet and I Googled half-life graphs, and I found this one, and I was like, oh my gosh, this is awesome. I can't wait to show this to students, because then they can see what half-life looks like. But then, guys, it was interesting. The year before COVID, which is the last year that we taught this material, I threw this graph up in front of a class of students, and they went, that graph is a mess. We understand about half-life, and this is not okay. And I'm like, what are you guys talking about? And they started to point out to me all of the errors and misconceptions and problems with this graph. And I was like, oh, shoot. Yeah, this thing is a mess. But then I decided rather than avoid it, I'm just going to let my other classes talk about it. So guys, I would ask you the same question that they posed to me. What are the errors or mistakes or misconceptions represented in this graph? Yeah. Yeah, right. So, guys, the years are in billions, and we're talking about 60 billion years. The time scale is inappropriate. Kind of. There are some radioactive substances that do have half-lives on the order of 4 and 5 billion years. But guys, it's 4 and 5 billion years. It's not 50 billion years. Absolutely agree. Guys, what else? Guys? Yeah, it was funny. They didn't even mention that one, but I noticed that as well. When I did this yesterday, I'm like, why doesn't the line go all the way up here? Why does it start in the middle of the ball? I agree with you. Yeah. Yeah. Guys, can I ask you to hold on for a second? Do you guys hear that humming? Yeah. It is driving me crazy. Oh, it's not. It's the amplifier and the speakers. Still there? How about that? Oh, yes. Okay. Sorry, guys. I totally couldn't focus with you because I was going crazy. Start again. So, what were you saying? Yeah. Are you going to draw? I think you should draw. What do you got?
So the graph starts right here.
Okay.
Right
oh,
here.
Wait, you're drawing with your hand. Yeah.
Right here.
Yeah.
It's still sort of accurate because it's actually at the top.
Okay, right.
But once you get here,
yeah.
those are like 3 and 2/3.
Yeah, right.
Because it's not actually a full log.
Okay, and so what should it actually be?
Well, it should just be 4 of these, but I guess not really. But
okay. So you got a problem with the fractions, right?
Pretty much.
Okay. Can I steal that back from you? Yeah, I totally love where you're going with that. So guys, what should these fractions be? If this is 10, this should be 5, and this should be 2.5, and this should be 1 1/4. So I totally agree with you that that's bad. But guys, any other problems with the spheres? This one didn't even occur to me. Go ahead.
Well, it's just like if it's really there's 11 billion years.
Yeah.
It should be completely filled in because it's not like the radioactive atoms just disappeared.
Yes, and that was the one that put me over the top. And I love that you picked up on that. Guys, and this was really the thing that spurred this conversation at the start. My students were like, wait a second. what happened to these? Because after one half-life, it looks like they just disappear. But that's not the case, right? The stuff is actually still there. It's just turned into something else. So I'm like, whoa, that's a huge misconception, because this makes it look like after a half-life, half of the stuff is gone. And the other, it's not gone, it just turned into something else. And if this is plutonium, then this is uranium. Absolutely, it doesn't just leave. So guys, anything else? Yeah. 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 All along. So after time 0, plutonium is turning, well, the other way around. Plutonium's turning into uranium. It happens right from the start, but after a half-life, half of it will have gone through that change. Go ahead.
Does the uranium decay through after?
Yeah, and that's brilliant. And I'm going to show you. So guys, Michael's question is really good. It's like, wait, does the uranium decay? Absolutely. What's its half-life? I'm going to show you at the end of the day today. It depends on the isotope. Some of it is 4.5 billion years. Some of it is on the order of days. I'll show you in a second. Go ahead.
So, because it's only like radioactive stuff that has a half-life, right?
Yeah.
So does it just keep turning into new substances until it's not?
Beautiful. Oh my gosh, you guys are amazing. Check this out. So, Jasmine, if I could paraphrase your question, is if radioactive stuff turns into radioactive stuff, when does it end, right? You ready for the interesting answer? Guys, remember the little paper that you wrote, the little questions thing? What about element 114? Why was element 114 the island that they were shooting for? It's stable. Remember that idea of doubly magic? It's got the right number of protons and neutrons to make this stable. Well, guess what? Lead is also doubly magic. All of the elements that are in this group are all doubly magic. And so, Jasmine, that's the answer to your question. All of the elements that are radioactive, that are heavier than lead, stop being radioactive and when they get to lead. Lead is the end of the road because it's doubly magic and stable and it doesn't break down anymore. Yeah, so we're going to look at that more in a minute. So guys, anything else there you want to pick apart? You guys are amazing. You guys good? Yeah. I know. Yeah, right. Exactly. It's not drawn very well to scale, right? Anything else? You guys are, yeah, guys. Is what?
So why don't we use half-life to measure caffeine?
Yeah, that's really, it's funny. You actually, that is, so maybe people don't know this. So caffeine has a half-life. And they talk about it that way in medicine. What is the half-life of caffeine, or what is the half-life of drugs? When they give us even antibiotics, they talk about the half-life of antibiotics, which simply means how long does it take for the caffeine or the antibiotics concentration in your blood to cut in half. So half-life doesn't just apply to radioactive stuff. Anything that breaks down over time, including caffeine, including antibiotics, we describe those things as having half-lives. And it's interesting, Kyson, that's the last question in the homework assignment today. And it'll talk about that as well. So, guys, anything else? Okay, so let's do this. Remember, this is the graph that my students tore apart, right? So after they tore this apart, I was like, okay, we need a better representation. So guys, I went out again and found this. I like this better. You? I like this one better. And the reason that I like this one better is the 10 by 10 grids that are up at the top of this representation. Because guys, when you look at this, look at what we've now got. So at time 0, we have 100 red things. Now guys, after one half-life, how many red things do we have? 50. But where did they go? Well, they turned into 50 gray things. So guys, what about another half-life? How many red things do we have? 25. How many gray things do we have? 75. Then guys, after another half-life, this should actually be 12.5. They didn't show the half of the sphere. And then this would be 87.5. But you can now see that after each successive half-life, half is gone, but it turns into something else like plutonium to uranium. So guys, this to me was a much better representation. So thoughts or comments on that one? Little better? Go ahead.
So on the last day of first term, we watched a video about how elements how it all came back from that.
Yeah. Yes. And that was actually Jasmine's question as well. And as soon as we're done with this, I'm going to show you a representation of all of that. You guys, please.
You know how long it takes for the cycle to completely end? So like all of it turns into red and all of it is not.
Remember the idea behind all of it. We never get to all of it. It's an asymptote, right? But what we can say is this, that some atoms go through all the steps instantaneously. Some of the atoms haven't even started the process. That's the idea with half-life. They are averages. Some of them do this instantaneously. Some of them haven't started, and some of them are trapped all along the way. So all that we can talk about is how long does it take for half of them to go through each step. And I'll show you more about that in a minute. So guys, you good with this idea, better representation? Let me show you how we're going to wrap this up then. And guys, this is important on the homework and on the test. You're going to want to write this down. Not this, but what's coming next. So guys, here's where we are. You guys are telling me that you're okay with this idea of 100, 50, 25, 12 and a half, and it just keeps going. So guys, if you're okay with that logic, we are going to use that logic to solve problems like this. Guys, do not write this down, but read it with me. This is the idea. Imagine that our rock of plutonium weighs 50 grams. And imagine that we could teleport ourselves into the future 72,000 years from right now. The question is this: what will that rock, how much plutonium will still be in that rock 72,000 years from now? Guys, do this with me, and this is going to feel childish, but do this with me. This is the way to solve the problem. In your notes, do this. Guys, draw yourself a plutonium rock. And then put the mass of the rock inside the rock. And we're going to be lazy with significant digits. Don't worry about it. So guys, that rock of plutonium weighs 50 grams. Now do this. The arrows represent half-lives. So a half-life for plutonium is 24,000 years, and then draw your rock again. Wait until you see the homework answers. I found some good-looking rocks. You're going to love it. So guys, after 24,000 years, how much of that rock is still plutonium? 25 grams. So guys, 25 grams of this is still plutonium. Now let me ask you an interesting question. What does the rock weigh? It still weighs 50. It's 25 grams of plutonium, and now it's 25 grams of uranium, but the rock still weighs 50. But we're just concerned with the plutonium, 25 grams. Now draw yourself another arrow representing another half-life. That will then be another 24,000 years for a total of 48,000 years. Now draw yourself another rock. How much plutonium is in that rock? 12 and a half. You see where this is headed. Now draw yourself another arrow. Another 24,000 years for a total of 72,000 years. Draw yourself another rock. And what is the mass of the plutonium in that rock? 12.5 divided by 2, which is 6.25 grams. And that is the answer to the question. What is the mass of plutonium that's in that at the end of this time? And the answer is 6.25 grams. Do you understand the logic? Guys, this is... Oh, go ahead.
So, and yet it's still way like a massive but
Exactly. It still will weigh, but we need to be careful, right? Because actually alpha particles have a little bit of mass, right? So it'll weigh really close to 50 grams. It'll be a little bit lower because the alpha particles take some mass with them. Even the electrons from beta decay do too. But it's going to be really close to 50 grams. But the plutonium will weigh 6.25 grams. You guys good on the idea? And by the way, guys, when you solve these in homework and when you solve these on the test, you're going to have room to literally draw pictures of rocks. This is the way to solve these. You guys good? We're going to do one more and then we're going to wrap up the day by talking about Kyson and Jasmine's question. So guys, again, don't write this down, but read it with me. So we have a radioactive element called molybdenum-91. And we let this sit around for an hour, for 60 minutes. So guys, the idea is the molybdenum starts at 100 grams. After 60 minutes, there's only 6.25 grams of molybdenum left. What is the half-life of molybdenum? Plutonium's 24,000 years. What is the half-life of molybdenum? Guys, here's the way to figure it out. Again, I know it sounds stupid, but it works. Draw yourself a rock. Now it's a molybdenum rock. And guys, the molybdenum, again, being lazy with significant digits, weighs 100 grams. Now draw yourself an arrow. Draw yourself a rock. After one half-life, how much molybdenum are we going to find? 50 grams. Then guys, draw yourself another arrow. Draw yourself another rock. Now it's 25 grams. Draw yourself an arrow. Draw yourself a rock. Now it's 12.5 grams. Draw yourself an arrow. Draw yourself a rock. Now it's 6.25 grams, which is the mass that we're looking for. So here's what we now know. In order to go from 100 grams down to 6.25 grams, it went through 1, 2, 3, 4. This went through 4 half-lives. But how long did it take to go through 4 half-lives? 60 minutes. So guys, if it took 60 minutes to go through 4 half-lives, how long is each half-life? 15 minutes. And that's the answer. Sorry, I ran out of space. But guys, that's the answer, is 15 minutes. Does that logic make sense as well? Yeah. Yeah, it is actually the half-life of... And so you can actually look this up. This table right here at the top of your thing actually gives, it's not exhaustive, but it actually gives the half-lives of a lot of elements. And I'm curious, I think this one is on there. What is it? It's molybdenum-91, and molybdenum is element number 42. So let me get in the light. So element 42, oh, you know what? The only one that's on here is molybdenum-99. But we could look it up. But yeah, it certainly could be the case. Yep. You guys good? So guys, let's wrap this up and then let's let you get your homework done. So guys, the last question, and you guys have been circling all around this. Kyson, even Michael do a level. Jasmine for sure. Where does this all end up? So we've got plutonium turning into uranium. That turns into thorium. Where does this all end up? Well, guys, I don't have the answer for plutonium, but I do have the answer for uranium. This is it. This is not on the test. You don't need to know or understand this, although there are ideas on here that you already know. But guys, this is fascinating. Let me show you how this works. Over here we have the atomic number. Down at the bottom we have the atomic mass. And this is where it starts. So guys, this nucleus is element number 92, uranium, with a mass of 238. Now, look at what happens to this. It goes through that kind of decay. Is that alpha or beta decay? That's alpha decay. And when it goes through alpha decay, the bottom number, the atomic number, goes down by 2. And the atomic mass goes down by 4. And in that alpha decay, this then goes from uranium down to thorium. So it becomes thorium with a mass of 234. Then guys, look at what happens next. It goes through this kind of decay. Is that alpha or beta? Beta. And guys, remember in beta decay, the mass doesn't change. Neutrons become protons. The mass doesn't change, but the atomic number goes up by 1. And so this goes from thorium to protactinium. Then it goes through another beta decay and it becomes uranium again. Weird, right? But it becomes uranium again, this time with a mass of 234. Then guys, after that, it goes alpha, 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 and it goes all the way down to element number 82, which is lead. But guys, this is not the isotope of lead that is doubly magic. This has got a mass of 214, and that is not doubly magic and therefore stable. So then it goes beta, beta, so its atomic number goes up to 84, and element 84 is polonium. Then it goes alpha, turns back into lead, then it goes beta, beta, turns back into polonium, and then it takes one more alpha decay, and it turns into lead with a mass of 206, and that's doubly magic, and that's where the story stops. So Jasmine, that's the huge answer to your question. But guys, Jasmine asked the question also, how long does this take? Guys, these are the half-lives of these processes. Let me zoom into this so that you can see it. So notice that each one of these decays is numbered. So this alpha decay right here has a half-life on the order of about a third the age of the universe. The universe is about 13 billion years old. And guys, this is about 4.5 billion years. So this first half-life is about the third the age of the universe. But then, guys, we go beta and beta. The first beta decay has a half-life of 24 days. The second beta decay has a half-life of 1.2 minutes. Then, guys, all these alpha decays, 250,000 years, 80,000 years, 1,600 years, 3.8 days, and 3.1 minutes. Those are the half-lives of those decays. Then, guys, you can go on from there and you can see how this all relates together. But, guys, the bottom line is this. Looking at this uranium, all of this uranium starts up here. And guys, some of those atoms in uranium have already gone through the entire cascade and they've turned into lead-206 and they're not radioactive anymore. Some of the elements haven't even started at all, and there are atoms all along the way stuck at each one of these intermediate steps, just waiting to take the next step. Guys, that's why uranium is both an alpha and a beta emitter, because there are elements all along this journey just waiting to spontaneously take the next step. Isn't that crazy? So guys, this was really a response to your questions. So are there other things there that you want to talk about? You guys all okay? Interesting, right? Okay. So guys, with that said, grab your homework packets and let's wrap up the day. Oh man, you have 25 minutes. You're not going to have homework tonight. So guys, looking at the homework packet, which apparently I can't find. Oh, there we go. So, gang, there's been a little bit of confusion, and I want to explain this to you. So, starting on page 1, this is the fission and fusion assignment. We did that. Then looking at assignment number 2, alpha-beta decay. We did that. If you haven't done it yet, it's due by Monday. Then, guys, assignment number 3. We did not do assignment number 3 in this form. But guys, if you look at the bottom of assignment, or at the top of assignment number 3, see where it says Nova Science Now? These are the questions that I gave you on another sheet of paper that you actually filled out and turned in. So guys, we did do the top of assignment number 3. You should have already turned that in. We're not going to do the bottom. Now guys, we're on assignment number 4. This is your homework for right now. Guys, let's get this done. This is actually well within your ability to complete today. So guys, let's get assignment number 4 done. When I see you on Monday, we'll turn this in. Any late homework has got to be turned in before that time. And then guys, we're going to take the test on Monday. Again, guys, please, please, please study for this test. Don't walk into this cold. It will trip you up.